It's a great pleasure to talk to you today. Thanks for the opportunity. This is, as defined as there's something curious, and I'm not sure what to make of it myself, but I just wanted to share these observations with you, which have been kind of tracking through various projects here as more or less a sideline, mainly, but it's just something that came up again and again. This is in particular the latest phase joined with Ola Vetters also here, and then some former PhD students are here. Okay, what I want to talk about are these runaway models. I borrow this term from I'm certain who coined it. I think it was in this paper by Casavareni during Loos and others. Who have observed this in that case kind of artificial tricky periodic situations, but I'll show where this happens in other contexts. Runaway modes in some form of effectively forced models are unboundedly and usually exponentially growing solutions. They therefore are accumulating energy. And in the cases that I'll talk about, these are exact linear modes, plane waves, monochromatic, or we can also do some superpositions. And also in some cases near initial states, so not only these exact, very carefully chosen states perform this growth, but also nearby. These for some time, this is always the case by continuous dependence, but it can even be for infinite time, so this can be stable. The term slightly, we still experience this growth. And well, I think one can also view this maybe as some kind of block of energy transfer, because these are modes on fixed scale. There's no transfer of energy into other scales going on. And here's just a couple of references where this has been observed before, and I'm curious if you maybe know more. So what I'm talking about, three examples. One is, very briefly, the troposphere wave model equation, where this happens. Boussinesq and related equations with kinetic energy, backscatter, which is topically in TRR. And then lastly, in the Fourier-Galerkin mode truncation of rotating convection. Okay, so let's start with this. This is a model devised by Constantine and Johnson for troposphere waves. It's kind of a long story of scaling and so on, and if you boil it down, it looks like this. It's not exactly horizontal and vertical velocities, but if you think of it like that, just take it mathematically as an equation, and the study that we were doing here was also mainly mathematically driven. I should say that anyway, I'm a mathematician, so when you turn off the forcing term k here, and you also look at vanishing this vertical velocity v, what you're left with is this Erg's equation type term, the diffusivity here, the alpha, and this term here. Now, if you then put in a solution of this form, it's an exact solution. It only depends on the x2 variables, so these derivatives here vanish actually. So you're just left with a linear equation. And then the linear equation just produces this exponential prefactor. And now if alpha is bigger than mu, there you go. Right? You have what I termed runaway here. It's an unbounded, exponentially growing solution to this non-linear system of equations. And from a mathematical viewpoint, this coming from nonlinear dynamics, this is really curious. Right? You have a nonlinear system, and you have an exact invariant subspace in which the dynamics is purely linear. It's like an invariant manifold in which you have linear dynamics. Right? This shouldn't happen. Right? Generically, this should not happen. But it does in this particular example and in the examples that I show. So I find this fascinating. Of course, if you would put on the forcing here or some funny boundary conditions, you would destroy this, right? Yeah, okay, that's kind of the weak part of this whole thing, right? This alpha is kind of an effective parameter in the derivation. And it's not completely clear what the size of it is. But in the model derivation, in the setup they do have examples where it is positive and good, where you have this relation. Yeah, so it does show up in the derivation and the modeling, and it's more for mathematical purposes that I show this here, because it's so simple that you can directly see it. So just to have some Yeah, and it's not so clear how to interpret it exactly. That's the weakness of this whole model, right? So I'd rather not go into that because I don't really understand it myself, right? We were looking at this model, I should say, with Paul Holz, PhD student, more from a mathematical viewpoint of PE theory. And then this kind of came up, there was just the idea, well, let's look at whether such solutions occur because I saw it elsewhere. And you take this ansatz and you say, whoops, okay, what's going on? And this is certainly scrutiny of the model, right? You can reinterpret this and say, hey, there's something funny going on with the model, and these parameters should not be allowed to behave like this.
You're imposing positive feedback.
Pardon?
You're imposing positive feedback.
Yeah, certainly there's a positive feedback. Yeah.
And the stupid solution is drop spatial dependence at all. And
no, it's
simply
spatially dependent.
Growth exponential with time.
Yeah, but it's spatially dependent, right?
Yeah, no, that's nice. But I think main ingredient is alpha u enhance u exponential with time.
Yeah, but it has this related.
Yeah, I got you.
Confusion, right? So, as I said, this is really just simple, just to get the idea. Right? This type of structure, you have that the horizontal velocity depends on the vertical variable, right? And there's this orthogonality between the direction of the wave vector and the wave amplitudes. That's what's always coming up. So, okay, now I want to talk about kinetic energy backscatter. So here's just my layman interpretation of why this is used. On the one hand, if we do discretization, particular for the climate models, is necessarily coarse. So you cannot resolve relevant subgrid dynamics. In particular, you're missing parts of this inverse cascade that has been repeatedly mentioned today. On the other hand, you'll have numerical solidity issues because in order to be able to simulate, that's what I do when talking to many people, I don't really do that myself. You really have to do somehow artificially high viscosity or strong dissipation to suppress the instabilities. And also in that way, small scale resolved dynamics is suppressed. And then the idea is to compensate this by a forcing term somehow in the equation, so-called subgrid parameterization, that should somehow simulate the effects that you have dammed out either by this over dissipation numerically or by the coarseness of the residue. Right? That's just my layman. I'm happy to take your opinion on this. This is just an introduction. And then if you perform this in a model in the sense of kinetic backscatter, the momentum equation on the right-hand side, you add such a term. Right? The rest of it is just standard or one way of formulating the primitive equations. And then there's this backscatter term here with the velocity. It decomposes into two parts, one viscosity parameterization, which in this case is typically hyperviscosity. And then there's this idea of re-injecting energy by negative viscosity. So in Fourier space, it looks like this in this so-called kinematic backscatter scheme, which just has constant coefficients for simplicity. This is the differential operator on the right-hand side, Fourier transform, we get this symbol. It looks like that. So large or high frequencies are damped, and large scales here are also just slightly excited, and somehow there is this peak here where you have effective excitation on this linear sense. And of course, this is something that is used for numerical simulation purposes, so it's implemented in a discretized mode. But in order to have some handle analytically, we take this as a PDE model. And then the simplest example is the 2D Euler equation, which is a subsystem on all of these systems here. So how does it look like in the 2D Euler equation here on the right-hand side? It's a classical situation. On the left-hand side, on the right-hand side is backstated. Then if you compute the energy equation associated with it, looks like this, where one kind of sees already this funny balance between the backscatter coefficient and the hyperviscosity coefficient. Now, it's not completely informative yet what it does. It's a bit more informative again to look at the spectrum of the Fourier symbol or the spectrum of the torus, say. And then you see that if the backscatter coefficient is smaller than the hyperviscosity coefficient, you have, because this is the first eigenvalue that's actually present on the torus, this is damped. All the higher modes of the torus also damped, right? This circle here is equation number 1 because I'm looking at the unit torus. So this continuum piece here is actually not visible because these large scales are not present. Right? The largest scale, the Mason scale, is this one instant. If it's this relation here, this first node, the Mason node, is excited or has growth, whereas every higher one is damped. And then if you have this relation, so backscatter is larger than twice the coefficient of the hyperviscosity, you have the Mason mode is growing and also the next one is growing, just to give you a little bit of a flavor of what this does. Okay, so let's look at this from the viewpoint of these normal modes or simple plane waves that I mentioned before. Right? This orthogonality relation is implemented here like so. We have y dependence, and then in the space variable, and the kind of velocity direction is just orthogonal to it. And then if you substitute this into the equation, this nonlinear term vanishes, just identically zero. So again, we have this subspace spanned by this prefactor A, in which the dynamics is purely linear. And you can compute what it does, and it's exactly looking like what we had before, only now in terms of this hyperviscosity versus backscatter coefficient. And yeah, maybe it's, I shouldn't have written it with a negative sign, but you can see here that if you have B is bigger than D, then you have this runaway. And in fact, you have the runaway on the subspace here of the so-called Stokes operator. These are exactly these eigenfunctions of the Stokes operator. And in fact, you can even do some certain types of superpositions to produce it. And this S of t here is denoting the solution operator associated with this nonlinear system of equations. So backscatter, of course, intuitively you would say, okay, if you have this on the eigenfunction space, the eigenvalue side that you have growing ones, it's no surprise that you have exponential growth somewhere, right, in small perturbations. The surprising thing for me is that you have it globally in time, right? It's exponentially growing unboundedly in the moments. So Paul has actually proven, in particular, Paul Holz's last one that's in his PhD thesis, a theorem there, which I just informally state here, that this is in the 2D Euler equation actually a dynamically stable phenomenon. So if you take any initial state near the span of this critical linear space, any initial state near sufficient close by in a certain function space, then this is subject to runaway. So it kind of picks up this exponential growth of one of these modes, and it just follows it, even though it's not even by itself initially clearly visible there. Yeah, so in simulations, this is one simulation that I've done here. It looks like that. This is a pseudospectral simulation of the 2D Euler equation with this backscatter with random initial data. So you see here the amplitude 0.02, this normalization as written here. And then we let this run for a long time. Yeah, this is a bit stronger than this statement because this statement doesn't really allow random initial data, but numerically it does work. Because what happens is this, there's this, also it's sometimes called selective decay. You might have heard that term, right? Selective decay, the largest scales decay slowest. And here it's kind of the opposite, that this backscatter kind of makes this selective growth. It is this largest scale modes that pick up exponential growth. This is at time 2000, which is not yet very large here, but it very, very quickly, as you know from numerical simulations, grows exponentially and then produces numerical error. So this is how this looks like in this context of the 2D Euler equation. And this implies actually runaway in a large class of models because they have this 2D Euler equation subsystem. For example, Navier-Stokes primitive equation, as I showed in the beginning, Boussinesq quasi-geostrophic equations. It also includes, just for using terminology that I guess is more informative for you, barotropic waves or flows. I don't really know the distinction between the two anyway, but barotropic modes, parallel Kolmogorov flows, monochromatic inverted gravity waves, and so on. You can find this phenomenon in these setups there, which I find curious, as I said. And it also persists, one can show, under forcing. If the forcing is kind of suitably associated with this runaway mode, it persists under that, as you might naturally expect, but it's not completely trivial because it's a nonlinear equation after all. Okay, there's another example, and maybe this flavor can come across a bit more, is the Charlotte equation rotating with backscatter here. And in this backscatter, I take the liberty to have anisotropy between the two directions of velocity. This is a little bit unphysical. Well, backscatter is probably unphysical anyway, but just to mention it, one of the motivations to allow for anisotropic backscatter is that if you do discretizations with an unstructured grid, you induce anisotropies. So that's why we took this there as well. The additional parameterization here. And then, okay, in this equation, how does the formalism go? It's very, very simple, as I said. Okay, we make a plane wave ansatz with the space variable psi here being the dot product of a wave vector K with the base vector x. Okay, so this. And then we are looking for velocity profiles which have this kind of modulation prefactor, which is real, and orthogonal direction of the velocity. And this is exactly this orthogonality between the K wave vector and this outer thing, which leads to cancellation. So this one here, maybe you can see it directly, that this is automatically zero for this type of solution, right? So they're always divergence free. You can also compute that this is always zero, which is what I said before, this nonlinear term vanishes. And similarly, this nonlinear term vanishes by the setup. So as I said, it's the same, just in different words, what I did before. And this leads then to the possibility to make such a monochromatic ansatz because you are ending up with a linear system. And what you then get is some algebraic equations, dispersion relation-like equations and compatibility equations between these coefficients here, but you have a chance because it's a linear system. And when you solve these, you find, I stay in the details, but you can identify runaway models for arbitrarily small backscatter. This is a set of solutions that, as I said, a small algebra there can be done. And this, in fact, persists if you add, in this particular example, we performed the detailed analysis for some bottom drag, for example. If you have linear bottom drag persists, and even for nonlinear bottom drag, you have cases of this phenomenon, although they adapt. But they do grow and they produce nonlinear states that wouldn't be there otherwise. Okay, then I come to the final example, rotating convection and Fourier-Galerkin truncation of that. So this has been spearheaded by Roland Welter, who's done this for 2D already. And this is kind of the extension of the first 3D. I should also say that there's predecessor work by During and Olsen who have done this in the non-rotating 2D case. And this is now the full 3D rotating case with no slip, free slip boundary conditions. So these are the Boussinesq equations written in this form, the viscous case with also temporal viscosity here, and the familiar parameters, at least in this scaling, they look like. I suppose many of you are familiar with this setup. And then, okay, I mean, there's this, if you have the non-rotating case, there's the classical starting point of roll solutions. Here we are interested in the dynamics overall, in particular in heat transport. I'm not going to talk about that here so much, but this we were hoping to find scaling laws for the Nusselt number. And these equations, in order to simulate them, you have to discretize somehow. And the Fourier-Galerkin truncation goes as follows. You first look for a suitable basis, and what you start out with, hence the name Fourier, with identifying okay Fourier models. So this is written in sine cosine because it's actually a good idea to do it for this nonlinear setup. Yeah. Then you try to find an expansion of these for the velocity field and the temperature buoyancy field. First of all, such an ansatz immediately gives you an index. I call this index in the following, even though it's a vector, for horizontal wave numbers, M1, M2, vertical wave number, M3. And then there are these P1, P2, and C parameters entering. I'm not going into too many details there, but that is discrete parameters such that one actually gets a basis for the boundary conditions, right? We have a free slip on top, bottom. Okay, so these functions should then satisfy these boundary conditions. and also must be divergence free in order to produce a suitable basis for the problem that we're considering. And then the next step is, okay, we're considering a finite expansion here in terms of some index set, which is abstractly written here, n script and ut and script and u tor and script theta tor. And the idea is that we're not prescribing yet what these sets are, right? But if you do it in standard, what you would do is you take a box in Fourier space, right, and you truncate somewhere outside a magnitude. But we on purpose don't do that yet. It's just a discrete finite set. Okay, associated with that, you have projection operators, which will produce the so-called truncated problem, which is this throwing in the trash bin we had earlier this morning. And anyway, so this is what the projections do. They project everything to zero that is not in these index sets. And that produces a finite dimensional problem. So you can write it as an ODE system with components indicized by this n. So I don't know how many modes there are. With a bit of counting, it's kind of a nightmare from the Fourier. But anyway, you get an ODE system at the end. That's what we call Fourier-Galerkin truncation, or a certain index set. All right, and the idea is now to look at the energy balances that happen in this process. If you go back to the PDE, this PDE satisfies certain energy laws. In particular, if you test with the velocity vector, u, right, you get the kinetic energy balance, which is this one here, right? So this, of course, produces the diffusion produces decay here, and then there's the exchange term coming in, which is velocity, and the vertical velocity and the buoyancy variable. So this is what we call an energy balance law for this equation. Similarly, you can find it by suitable testing for this variable here, which is corresponding to potential energy law. So you have a kinetic energy law, you have potential energy law. And the idea is now that, okay, there's also another one, sorry, the vorticity law here, which doesn't really enter into the analysis that I'm presenting. But first, we certainly do. In particular, the first one is kind of easy because this is satisfied for any truncation by orthogonality relations in this following sense. So if I take this here and look at the truncated version of it, then it is valid. However, if I take this one here and look at the truncated version of it, is in general not. That's what I want to go to here. So how does it work? We take the truncated model, we perform similar testing. In particular, for the potential energy law, you get this here. And now it's not clear that the choice of modes that you did in the truncation satisfy this relation automatically. Yeah. We can show that this truncated potential energy balance law is valid if and only if this relation here is satisfied, where this bracket here always means averaging. Now, it's still not completely obvious what this means, but if you look carefully, you can identify that this equation here implies a certain selection criterion for the Fourier modes that you have to include. You can translate this into a criterion for the selection of the modes that you have to do in your truncation. And this is not new, right? This in principle has been done before, as I said, particularly by During and Olsen. But what's new is that this is done in this more general context and in this systematic way, and we can then even show that if you satisfy this law in your truncated model, then the associated truncated ODE has global solutions, even a global attractor, as we say. And that's good news for the well-posted viewpoint, right? And also for physical meaningfulness. It's good news. Now you can turn it around and ask, okay, what if you don't satisfy this? Does it have any impact? What happens if you take a so-called what we call energetically inconsistent truncation? And it turns out that there are various types in which way you can break this consistency. There's one which I don't explain in detail, but I first want to mention that Howard and Krishnamurti in '86, they did a specific kind of, in this viewpoint, easy, simple truncation, and they noted that this can have runaway. And this was also repeatedly observed by Truffaut and Horton in 1996 and by Bering Olsen also in all these non-rotating 2D cases. Okay, and here in this paper under review, we have the following result. There's a certain, I don't explain exactly what it is, I'm sorry, it's tricky, but I can say something heuristic about it. Let's just read what it says. So suppose you have a truncated model where you choose these index sets in such a way that you create a certain inconsistency. Then runaway modes occur for any fixed value of the rotation parameter and for all sufficiently large Rayleigh numbers. And you can even say, okay, where does this happen? This has to be kind of sufficiently large. You can kind of see here that if you have a truncation where this critical mode, which is performing this inconsistency, this associated with this M, if that is given, then in order to see the growth associated to that, you have to take sufficiently large Rayleigh number. And I emphasize this because it's kind of, I think, intuitive for many of you that if you take a truncation and you crank up the Reynolds or Rayleigh number too high, you can't expect the numerical result to be valid or very valid. At some point, you lose it because the higher the Rayleigh number or Reynolds number, the more turbulence you excite, the smaller the scales that are relevant. And if you don't have them in the model, you can't really see the correct thing. And here there's kind of a quantitative version of this. That's what I find, I think. Okay, so what about this inconsistency? Well, let me just say so much that if you take your standard favorite box type truncation illustrated here, which is the standard thing to do at the beginning, then such inconsistencies are everywhere. There are many, many inconsistencies, all modes which have weight number bigger than M over 2, which is the truncation, are affected. And the reason is, roughly speaking, that if you take two of such modes and you multiply them, you're adding up the wave vectors, and they lie outside your box, so they're projected away. And that means that the interaction that they produce are not balanced by an associate mode in your model. So the energy that goes into such modes and such interactions is not damped. That's one way to think of this. And a fun fact on the side here, actually, that we can have observed, if you take the following situation, you take your box model, that's the other thing, part of the story, you can also recreate consistency. So you start with an inconsistent truncation, and then we can tell you a recipe of what to do to make it consistent. And in this particular case for the box, what you have to do is you have to add vertical modes. That's the only thing that's kind of relevant. And if you do this, so you take your box, augment the correct mode so that it's consistent, then you produce a system in which you have many, many Lorentz 63 submodels inside as kind of 3D invariants of systems. I think this is more kind of a curiosity again, but I wanted to mention it because I like it so much. Okay, that's all I wanted to say. Thank you very much for your attention. Here's kind of a list of references associated with that. Roland, forgive me, I forgot to mention your paper was 2D, so there's another important paper. Thank you very much.